There we go. So our first speaker is award winner Ian Robinson. He's going to be speaking about a new type of X-ray diffraction, followed by our next speaker is Dmitry Talapin. There's Dmitry, and you're going to be talking about making QDs and salt melts, if I'm not mistaken. Is that what yeah. It's fascinating work. Our next speaker, I just met Efrain Rodriguez at the University of Maryland. And he was just informing me about neutron diffraction. I just learned quite a bit in our last 10-minute conversation. And our last speaker will be Suying Kwek, did I say that right? From National University of Singapore, which is a wonderful facility. Our first speaker is Ian Robinson, who is this year's APS Arthur Holly Compton Award winner. And we have a plaque for Ian, if you want to come up here. And I think this is for the website, by the way.
Yeah. And this is for the photograph.
Here we go. Proud to present this to Ian, our award winner. So Ian developed a new type of Bragg diffraction imaging, which has been incorporated into the APS upgrade. So with that, let me just let our speakers, just a few folks can police yourselves and just come up and introduce yourself, and I'll stay out of your way. And with that, let's thank our first speaker.
Yeah, I'm going to wind back first and then share screen. Yeah. So, can everybody, oh, I've got my microphone on. I need that off, otherwise it's going to.
That's your speakers on.
Speakers on, yeah.
Okay.
There we go.
Right again.
Okay. Very good. And hopefully we've got a laser pointer. Excuse the video. I can turn off the video. So I'm going to have to stay near the microphone here because it's not portable. Can everybody hear me? I had a little bit of trouble yesterday hearing, so if it is difficult, try to let me know and I'll stay as close as I can to the microphone. But I do tend to leap around a little bit when I get excited about my presentation. So if I start doing that, please stop me and let me come back. So I'm delighted to receive the Compton Award this year, and the reason being that Compton was one of the heroes of X-ray scattering, and one of the big sort of founders of facility-type research, long before synchrotrons were invented or put into public service the way they are today. But I wanted to tell us a small related story here. The other big hero of X-ray scattering was Lawrence Bragg. And Bragg is the first word that appears in my presentation here. The idea of calling this technique Bragg CDI was not mine. It came from somebody in the management at Argonne. I suspect Stefan Vogt, but I'm not sure, because they wanted to put a label on the beamline that was different from all the other CDI beamlines that were at Argonne, and so we became BCDI, and everyone else got to keep the name CDI. And they've now almost completed a BCDI beamline at Brookhaven at the NSLS2, but its name is CDI because they only allow 3 letters for the beamlines. So anyway, Bragg, I could spend the whole lecture talking about Bragg, but was clearly one of the founders of structure determination using X-rays, and we're continuing that tradition with the current facilities. Okay, so how do I advance? Okay, so the talk is pretty simple. It's going to be mostly historical. A lot of it will be before many of you showed up here, and I'm sorry about that, but it's also my one and only chance to talk about the old days. And so I probably won't do this again. I've been able to dig out some slides from 20 years ago, and I'm going to tell most of the talk will be quite old history, and then I will address the questions of current and future directions right at the end. But I think you're hearing that from many people around here, so this will be slightly different. Okay, so this is actually quite an important slide. This is half of the story from my perspective of where Bragg coherent diffraction imaging came from. I think we could all agree that it goes back to a previous Compton Award winner, Mark Sutton, who did a pioneering experiment that was published in 1991. And the thing I remember about this, the things in red I'm going to elaborate on later on in the talk, but I did want to capture the early history here in a single slide. I remember when this experiment took place because it was on a Saturday and it was at NSLS, the old synchrotron, and the place to develop the photographs was right next to our beamline X16. And I remember bumping into Brian middle of the morning on that Saturday. I don't remember the date, but Brian is smiling, so he may remember. I don't know. But he showed me this photograph, a piece of dental film with a bunch of spots on it, and I simply could not believe that this had come from the diffraction of a copper-3 gold sample that they had at X25 on that day. And well, the rest is history, as they say. This was the beginning of the technique, and this does relate directly to Compton, because Compton, one of his ideas was to take the well-known knowledge of optics from the 19th century and take it forward to the 20th century with the particle wave duality and all of these things, and showing that things like cosmic rays were due to particles and not due to photons, and things like that was all part of Compton's career. So the idea of taking an optical experiment, which was a classical optical speckle experiment that I didn't know anything about, and turning it into an X-ray experiment was very novel at the time, and that led to the developments that we're seeing. And then fairly soon after that, ESRF came online, and we, Brian, myself, Mark Sutton, and a few other people all pleaded with them to get 3 days of beam time early on in the operation there. We worked with Jens Hals Nielsen at the Troika beamline to do some pioneering experiments to explore this idea of coherence, which was already starting to sort of get caught on. And very soon after that came the paper of Steve Dierker, which was the first demonstration of XPCS, the photon correlation spectroscopy. And in fact, the speckle community, as it was at the time, was thinking that XPCS would be the future. And in fact, I was following along with that as well. And we were assuming that we would see XPCS-like phenomena in diffraction from solids. And it turned out to be a little bit different. But anyway, our first experiment, which was done during those 3 days at ESRF, was published a couple of years later. And I'll show that briefly. And then we started started thinking about the technology that would be needed to develop the method. And we started with these rollerblade slits that I'll show you, and then we started on some of the computational methods that were needed to work with the coherent diffraction data, and I'll show you that. And we've got our first reconstruction, which was 97, that I'll show you. And then we started looking at surfaces and interfaces using this method. And this was all the time while we were continuing to use our tools of the time, the surface diffraction techniques. And that was our main activity. This was all sort of done on the side at the time, but we built up a case for building a beamline here. And part of that story was looking at the kind of the shape of the speckle that you get from copper-3 gold, and we then started developing in a serious way the technology to build a beamline. I'll show you that. We've got the first application of the phasing software to nanocrystals, and then this was another big event that we all enjoyed and took part in, where we got theoretical people working on inversion problems together with some of the experimentalists that were interested in the diffraction. And there was the first of the coherence conferences, and now we've had, I don't know how many, but about 10 coherence conferences since that, and it's a sort of growing community of interest in coherence. And then the big day for me was May of 2001, when we first got light into the beamline, and then, well, the rest is use of the beamline, which has gone on for 20 years. Okay, so this is the piece of dental film that I was referring to before. What Mark and company were doing were looking with pinholes at cutting down the size of the X-ray beam. You take an wiggler beam in those days, and cut it down to a few microns with a pinhole, and you scan another pinhole across it, and you can see side fringes due to the diffraction of the pinhole. This would be the far field diffraction of the pinhole, which would be a circular ring pattern. And you can see that with the pinholes. And then if you put in a sample that's disordered, this was a crystal of copper-3 gold, and look at a Bragg peak, this is the very first BCDI. This is a speckled diffraction pattern coming from the disorder that's present in the spot that's illuminated on the copper-3 gold, interfering with itself and leading to all these complicated features that appear in the diffraction. And this is transforming. So this developed the whole field. So our first experiment was to look at a multi-layer sample, and we used one of these pinholes to define a coherent region of the beam, something like 5 microns in size, maybe a little bit less. And then we look at the far field diffraction from this with another pinhole. We didn't have CCDs even at the time. We certainly didn't have these big Eiger detectors that we use today. But we would scan a pinhole across this, and when you scan the pinhole across, sure enough, you see interference from the different regions of the sample. And by modeling it and cranking very hard on a simple sort of calculation, we could get some reasonably good fit to the distribution of speckles, and that corresponded to a distribution of the heights of the regions, the different regions of the multilayer that we were looking at. And this fits into the then view of the world, which was the world of surface diffraction, where there were people interested in the small angle region and the reflectivity region of reciprocal space, and there was a community interested in looking at extended reflectivity going up through the Bragg peaks. And then there was the truncation region, where we would have streaks of diffraction and superstructure reflections, and all of these things were newly accessible to the coherence methods. And so one by one we started to look into those. And some of them were interesting and some of them were less interesting. So if we looked at rough surfaces, then the classical view of a rough surface would be that you'd have some sort of correlation length and some sort of roughness, and that would appear in the classical picture of averaging over the coherence as a diffuse scattering coming from the distance scale of the sample and some sort of specular peak that would come from the average structure. And when you look at it with coherence, you would limit yourself to just a small patch of the sample with a pinhole, and then what you would see is the interference, the coherent interference that would lead to maxima or minima of the diffraction. This is what you can then use to determine the structure of the surface in this case. And the big breakthrough came with the development of one of the optics algorithms developed by Jim Feenup in the 1970s. And this was work done by Ivan Vartanyans, who was a visitor with us in Urbana at the time. And we got nice reproducible data from one of these silicon wafers, which had just a couple of peaks in it, but it was enough to give us the information about the surface morphology. And he put that into one of these inversion algorithms where you assume the profile of the beam to be some sort of box like this, and out comes the height of the surface reproducibly, as in this case, just a kink where the surface changes slope. But this was a demonstration of how it works. So this is the coherent diffraction. What greatly changed the awareness of the work was this paper by John Miao, who was a student at Stony Brook with Janos Kurtz. He was also supervised by David Sayre, one of the founders of crystallography, who was at IBM. He was the author of Fortran, by the way, one of the authors of Fortran, and he made his salary from writing and looking after Fortran, but he was interested in crystallography and is well known for that. But he had always said, and I remember when I was a student, David Sayre giving talks saying, if only you could measure in between the Bragg peaks, then you would be able to invert the diffraction and just get a structure without having to solve the phase problem in crystallography that way. And this was a demonstration of that. So John's experiment was to look at a set of dots on a silicon nitride membrane, and you see the diffraction. This isn't a very good reproduction of it, but this was the printing quality of nature. You can see that there's a lot of speckles inside here, maxima and minima, and you can invert that using one of these inversion algorithms, and you get, sure enough, you get an image of the pattern that you created. And this had an enormous impact on the field because it said that this would be a general structural method that would be available to all of us. This is the modern version of it. So you use a Fourier transform to go from real space image to reciprocal space. What you measure goes into the algorithm in reciprocal space, overwriting the amplitude of the diffraction, but you don't know the phase, so you can't touch it. And when you inverse transform that, all the errors in the phase are going to show up as errors in the image. But you then apply some sort of real space constraint, which is this pink support box here, as it's now called, the box that Ivan used in his surface reconstruction that I showed. That support cuts off all the erroneous part of the real space image, and then when you come back to real space, the phases are better. And then when you overwrite the amplitudes with the data, you can iterate, and this is called the error reduction method. And an important advance on that was Feenup's hybrid input-output method that's still used today as the sort of standard approach to inverting these diffraction patterns. And there was a lot of theory that was discussed at this coherence conference that said that these inversion problems in 2 dimensions and 3 dimensions are generally unique. But the subject of uniqueness I'll come back to right at the end of my talk, because it's true under some circumstances, and we still don't know quite how general that is. Okay, so continuing our experimental front, there's another story to tell here. This was an experiment done by Garth Williams and Mark Pfeiffer, who were 2 students of mine in Urbana at the time. And I remember we sat down at one of our group meetings and said, well, we can get speckle in the diffuse scattering associated with reflectivity. And in fact, they asked the question, what would happen if we looked at the Bragg diffraction of one of these samples? And I said, well, it'll have truncation rods and it'll have diffuse scattering associated with it, and it should be an exact copy of what goes on at the origin of reciprocal space, which is all the surface scattering that we were talking about. And if you do it, well, so the experiment is you take a gold film and you heat it for a long time at 1,000 degrees, and it de-wets into these little rivers, and then you get isolated particles. And we put one of these into the beam at 33 ID, which was already operating at this time. This is the shape transform of a piece of theoretical object here, and you can see it's got these streaks perpendicular to all the facets, and these are the beginnings of the truncation rods that we were familiar with. But you also get all this modulation where they interfere with each other and lead to maxima and minima. And so we measured that, and in fact we were able to get fairly good reproductions of the two-dimensional diffraction pattern. This was the Princeton Instrument CCD that we had just bought, and this is done at 33 ID, and we could get really quite good agreement with those diffraction patterns. So this was where the group meeting turned into a real experiment that got published. And then we went beyond that and started to say, well, if you can do it in 2D, you can also do it in 3D, because you can take the Ewald sphere and you can cut through these three-dimensional Fourier transforms of the shape of the sample, and this is what you measure. It just played itself, but you can stack these together and get a 3D diffraction pattern, and you can invert that, and this is the result of the inversion. So you can see that we can divide it up into slices, and we get three-dimensional slices of an X-ray image measured through the Bragg peak of the shape of this gold crystal. Okay, I'll come back to that a little bit later as well. So moving towards the hardware needed to do the experiments, it was clear that you needed pinholes to define the beam. The undulators, the DSRF and APS have, for hard X-rays, 8 kilovolts. They have about 1% of the beam is coherent, and 99% is not. So you have to cut out just the coherent piece. At least that was what we thought we had to do at the time. And to cut it out, we developed these rollerblade slits, and this was a very elaborate design that was achieved by Alex Nosko in his machine shop, where you can pass water cooling through the slits. We were thinking that we would use this with the pink beam from the undulator, and so we needed the cooling, and you had to polish the blades very carefully. But the idea was that if you rotate these two cylinders against each other, you can make a variable-sized slit. And when we did that, we got a surprise, which was that you get beautiful fringes from it. This was measured at X25 of NSLS at the time, but the fringes on one side were more rapid than the fringes on the other side. And the reason for this is explained in this paper here. It's a parallax effect. If you look from one side, the two blades are not in the same plane, and so one side, the slit looks bigger than the other side, and that effect shows up in the diffraction of the slits there. But nevertheless, we have a way of making an adjustable sized beam with this. And you can see it was really quite a complicated design, and it was something we were quite proud of at the time. But we've actually we used it for a couple of years, and well, I'm talking about the early history here. We're not going to talk about the present day so much. But one of the things we showed was that it's very important to get close to the slits if you want to see these kind of diffraction effects. And this is classical optics. So if you sit one distance away from two of these cross slits, you get a sort of 4-peak Fresnel diffraction pattern, and here you get a 9-peak Fresnel diffraction pattern. And if you look in the textbook, this is the classical optics book that we taught from, you see exactly the same thing. You can see that in the near field of a slit, you get this optical interference, which sometimes gives you 4 peaks and sometimes gives you about 9 peaks. So you know, this is not a surprise, but it was very nice to see it with X-rays with 1,000 times shorter wavelength. Okay, well, I've already gone through this slide, but I wanted to show you where we've got up to in the talk. So I've talked about all of these things up to here, and now the next thing I'm going to talk about is that we actually did get the money together and get the organization together. This was in the days when APS was still a user facility where the users had to build the beam lines and not the facility. And so through the UNICAT consortium at the University of Illinois, we actually put together a case for building a beam line at Sector 34. And this is the best drawing I could find of it, because most of it is in paper documents that I've not kept careful copies of. But we have one of the standard 33 millimeter, I can't remember, the original undulator A's that is the source point here. And we had the very clever idea that because we only need 1% of the beam, we can actually take 2% of the beam and feed 2 separate experiments from the same beam, the same undulator. And all we need to do is to split the beam into 2, and we can run 2 simultaneous experiments on that. And the natural partner for that was this so-called microfocus diffraction experiment that's now the white beam Lauer experiment that was developed by Ben Larson and somebody remind me. Gene Ice, thank you. Yes, at Oak Ridge, and they had been this instrument that they built had been moving around a little bit because they didn't have a home for it, and we found this natural home where we could take the second % of the beam because they had coherent focusing optics that needed only a fraction of the beam to operate, and we could run the 2 in parallel. And the way we did it was by making this beam-splitting mirror that we spent a bit of time working on. This was the work of Kurt Kenny Benson, and the idea was that we would put the mirror partway into the white beam, and because it's white beam, we assumed we had to liquid nitrogen cool it, and so we set up this tank above the A hutch that would drip feed liquid nitrogen into the mirror, and we hoped it would not cause too much vibration. Unfortunately, we did get some instability due to that cooling system because it's a single point mount, and we lived with it for 22 years basically because it never really went away. But the original design was that we would have this beam splitting mirror, and we kept the mirror right through the history of the beamline. So quickly to go through the items in the BCDI hutch, we've got this very nice 6-circle diffractometer developed by Bicor Control, which was taken over by Newport. And it's got this big heavy detector arm, so we can put a detector a couple of meters away from the sample. It turned out to be a little bit difficult to reconfigure the detector, and so Ross developed an alternative detector arm down the road, but this was the original design. We also had a Kappa diffractometer here, which allowed multi-axis orientation of a sample that was in the beam, and that also got replaced. In fact, here's another view of it, showing one of the consequences of splitting the beam is you've got a second beam line going through your hutch, and so you have to stay 15 centimeters away from the an operating beam line for all your experiments, but that was actually not a problem, and this diffractometer was designed to fit under the beam line and work in the available space. So the change that took place there was we found this was hopelessly inaccurate for doing the 3D kinds of measurements that we needed. Plus, as you'll see in a moment, we wanted to connect it to a vacuum chamber, and so all the distortions of the vacuum forces were also limiting the functionality of this diffractometer. So we had the idea that we had these old Huber stages sitting in the closet. There's this one here and this one here, and we threw these two together, took out the diffractometer, and basically never went back. So we went down to a much more crude kind of diffractometer, but one that was able to meet the specs that were needed for the measurement. The other slightly unusual development was that we had a water-cooled monochromator. We ran out of budget and we couldn't afford one of the fancy Kozu liquid nitrogen-cooled monochromators. We'd even said that we would work with only pink beam at one point, and we gave up on that and made a copy of one of the Brookhaven monochromators that was designed by Paul Foos, and installed that in the B hutch of 34ID. And you can see here the way to get around the unavailability of liquid nitrogen cooling, which was just too expensive for us, was to use diamond crystals for the monochromators. So we had water-cooled diamond, and we found that we got really bad wavefronts coming from this, and we investigated this, and we found that the diamonds, they were from Sumitomo. We still got them, I think, but the diamonds were full of defects, and you could see all these little defects that you can see in topography. This was topography measured at the 33 BM topography station that was already running at the time. This was affected by the clamping screws were causing a distortion that led to this bright region that appeared in the crystals. But even without the clamping screws, you still get all these fine features due to the growth of the diamond. And so after a few months, we gave up on that and just replaced it with silicon and got away with it. So the water-cooled silicon, because the monochromator was far from the source, and especially because we'd slit down to a small beam size before reaching it, the power level was manageable. So this should be the midway through my talk, and I think I've got 10 minutes left, is that right? So I'm going to have to hurry up a little bit. But anyway, this is, if you can read it, is the logbook. Wonsuk gave me a copy of this, my handwriting, on the 10th of May, 2001, where we got a burn paper with the first beam on it. And this is the current detector running on a Bragg Peak, looking at the BCDI pattern in May of 2023, when they pulled the plug and went into the shutdown for the APSU that we've heard all about. And the data is perfectly valid and reconstructs to make an image of the sample. Okay, so I'm going to go into the second part of the story. So this is part two of the development of the method, and I'll just basically read it. But an important step was to edit the support, and this was the method developed by Marchesini, where you can shrink the support to match the shape of the crystal. And this, for difficult samples, made the difference between working and not working for the algorithm. We also developed coherent methods for looking at the small angle scattering, which I'll show quickly. And we did a very important experiment on lead crystals grown in the beamline, and we developed refraction correction. And then that same year, the very first tychography experiment was done by John Rodenberg and Franz Pfeiffer in PSI. And as many of you know, the tychography is it's a much more successful branch of coherent diffraction imaging than BCDI, because there's now 3 or 4 beamlines at APSU that are all dedicated to the tychography. And this would be a totally different talk, but this was the branching point where tychography suddenly appeared on the scene and has taken off since then. So the developments for us were the exploration of the strain direction that's accessible. I'll show you where that comes from in a second. We introduced confocal microscopes for 3D alignment of the samples. We developed the idea of propagation uniqueness, which is part of the problem of the Bragg method. And a way of correcting for the partial coherence. We've also done XFEL experiments, and we've started to use artificial intelligence methods for the phasing. But this latter part is beyond the scope of my current talk. So the next thing I'll talk about, I'll be a little bit brief, is the idea that you can look in a reflection geometry at a rough surface, and you look below the critical angle, and what you see, I should skip that. What you see is this Yoneda peak, which is parallel to the horizon of the sample, but you can see from this nice example that it's extremely speckled, and that speckle comes from all the grains which are present inside the crystal. And this is something that we discovered and published back in, when was it, 2003 or 4. But we didn't follow up on it because we got so interested in the nanocrystals. But this is something I'm planning to do again fairly soon. The other development came from Peter here, who had made a modular KB optic, and we didn't really expect this to work, but we bought from University of Chicago one of these focusing systems, and we put it in the beamline. And we found that we could take much more beam and put it onto much smaller crystals, and we looked at synthesized silver crystals that are made by this chemical method. And they're about 100 nanometers in size, and we get beautiful diffraction patterns from these. So the KB optics is able to preserve the coherence in a way that we didn't expect, and this is now standard practice for the beamline. And that diffraction pattern was even reconstructed in the way that I talked about before. So we use this today. The standard way of using it is we look at a powder of nanocrystals on a substrate. We get powder rings, but the powder rings have got individual peaks from individual crystals, and each of those peaks has got these fringes on it that tells us that the image is coherent. And this is our sort of off-the-shelf inversion method. We take a 3D stack of these diffraction patterns and invert it into an image of a crystal. And the aspect of that which is unique to the Bragg method is that because of the momentum transfer, we're sensitive to the strain, and that appears as the image is complex, and it's got a phase which changes in different locations of the sample. And the reason it changes is that parts of the crystal are strained, and you can think of that just as rigid body shifts of pieces of the crystal relative to the others. And every time you shift a piece, you change the phase of the X-rays diffracted from it by the little red piece in here. And if you work it out, it's just the Q vector projected onto the displacement vector. And this gives you picometer sensitivity to the distortions of the crystal. And we first saw that in this in situ experiment that was done in this chamber here with a beryllium window that's covered up here. But this was the thing that we spent our initial investment in the beamline to get working. And it was really only used for this one experiment. So inside that vacuum chamber, in the coherent beam, we have a sample stage which can heat the sample up to high temperature. And we evaporated lead onto the sample, and we could see in SEM afterwards that we got these nice nanocrystals formed of basically spherical lumps of lead that are crystalline on the substrate. And they gave these beautiful diffraction patterns that made a good part of Garth's PhD thesis here. And they inverted. This was the Fourier transform inversion method that we were developing at the time, and you get an amplitude image in cross-section here, and you get the phase image here, which shows this sort of these clouds of phase that are present inside the structure. And you can interpret the shape of the crystal. Mark did this as part of his PhD thesis. You can find all the facets and you can index them, measure the angles between them in 3 dimensions. In order to do this, you have to perform a coordinate transformation on the data, and we're learning how to do that at the time. And that allowed us to get valid 3-dimensional information in real space. So you get this pattern of facets on the lead crystal, and you can understand what you see is this cloud of phase at the bottom, which is where the crystal touches the substrate, and the crystal is being deformed by contact with the substrate, and you can model it as an elastic field using finite element type methods. Then another key step was to realize that this crystal was almost a millimeter, almost a micron in size. And if you send an X-ray beam through a micron of lead, you actually get, just due to refraction, you get a significant phase shift. And so if we're looking at the phase of the image, you have to actually correct for this, refraction effect. So here is the refraction effect mapped out, where the deepest parts of the crystal get the biggest phase shift, and the top of the crystal gets no phase shift. And you apply that to the image, and this is the one that was published in the Nature paper. This is the corrected version of it. The phase actually gets stronger associated with the strain, but also the surface sort of cleans up, and you can see that there's a surface strain that's present as well. So this was one of the natural steps that was required. So I'm going to be out of time. So let me I was going to show this recent achievement, but since we're mostly working on the past, let me talk about the future. I've just got a couple of slides left, and then we'll be done. So the development of this strain idea is that it's also an opportunity to look at domains, and each domain is going to have a different phase shift because it's got a different crystallographic relationship between the different pieces of the domains. And this is very recent data. This was an experiment done at Petra last November, where we were looking at solid-state electrolyte materials. This one is one of the Nasion materials. And you can see it's got this very complicated grain structure that you see in the shape. And if you take a cross-section, you can see all of these phase-shifted domains inside it. But the uniqueness of this solution is still something that we're working on. But I believe that I'm planning to spend the next couple of years looking at these materials and trying to use it to develop an understanding of how solid-state electrolytes work, because it does look like these domain boundaries could be an important part of the ion conduction properties of the material. And they're basically impossible to see by any method except PCDI. So I think we do have a future. So wrapping up, and sorry for running over, I'll just leave this up so you can see. I hope I've caught everybody that's been involved in the development of the method over on the left. We had grants from NSF and DOE and the state of Illinois through the UNICAT consortium. We had these people working at Illinois and UCL, and then a more recent list of people that have been developing the method through Brookhaven and Argonne. So thank you all for listening, and I hope you've got some questions.
Hi, Ian. Thanks a lot. Great talk. Maybe you could give us some ideas. How are you going to approach this issue of these domains? And do you think it's going to be an experimental approach or an analysis or a combination of both?
How are we going to solve the uniqueness problem?
From the domains, the complex domains.
The domains. It's going to be all of the above. I think part of the answer is going to be we're going to have to fudge it, which is we're going to have to admit that there will be multiple solutions to the phase problem. But if you look at those solutions, they're very, very similar to each other, and you can find common features among them, even though you can't say this is the right one and this is the wrong one. There are common features like the domains I just showed, which are always present, and so we just need to sort of work on it that way. There's a paper that came out 1st of May in JSR from Hyunjung Kim's group that shows that if you average a lot of those solutions together, you can actually improve the image that comes out. We'll look into that. But this is one of the reasons why tychography has sort of taken off more than BCDI, is because we still have this sort of long-lived uniqueness question that's present.
Do we have time for one more question?
Tony Rollett from Carnegie Mellon. Yes. Thank you very much for the historical background. With reference to the Yoneda peak from a polycrystalline sample, is that speckle in any way something that could be forward modeled so as to learn something about the polycrystal structure?
I'm not hearing you very well. I didn't put my hearing aids in because it affects when I give a talk. But can you speak up a little?
I was talking about the Yoneda peak.
Oh, the Yoneda peak, yes.
Yes, and is there reconstructible information in that speckle?
Probably not. I think that's going to be, the things I'm imagining to do with that is to do the XPCS type experiment, which is you look at the speckles, and then since it's the surface of a thin film, you can actually do things to that surface. So one of them would be you could excite it with a laser, and we believe that the laser creates electrons which will go to the grain boundaries in that sample. And so we should be able to see XPCS-like response of the speckles to laser excitation, but we could also do chemical excitation, we could do alloying and de-alloying type experiments, and all of these things would be seen through the XPCS information without having to invert the diffraction pattern to images. But it might be possible to invert them. I haven't thought about that.
All right, let's thank our speaker.
Yes, see you then.
This is your pointer.
Thank you.
Oh, you have one, okay.
Nice talk, thank you. Can you please tell me how can I connect to? Zoom I do?
Okay. Do you have the meeting invite link?
No, I'm not sure.
Let me grab you the code.
Okay. Yeah, I will open Zoom. Oh yeah. I would need to connect to Wi-Fi.
Do you have the guest login?
I don't.
Okay, we're gonna have to create that real quick. Sorry. It's gonna have you make a username and password real quick. So register.
Okay.
Spelling.
401.
Just say yes.
Recording in progress.
Terrific. Thank you very much. I'm sorry for this small delay. And today, well, it's a great pleasure and honor for me to be here. Let me talk about our recent work in the development of novel synthetic methodologies for materials that kind of sit at the interface of traditional chemistries, traditional chemistry subfields. Oops. Yes. So for many years, we've been trying to develop methods that allow us to combine chemistry, to combine complexity of molecules with robustness and rigidity and conductivity of solids. And the best way to do this is to use different platforms like metal organic frameworks, or more recently discovered lead halide perovskites, and also nanomaterials, which these are kind of materials that are difficult to kind of present as a classical examples of like inorganic, organic, solid state or molecular species. And here I want to demonstrate first I will talk about nanocrystals, which are really these interfacial materials that are hard to classify as solid state or molecular organic and inorganic. And it's a very rich field where the inorganic, this core, crystalline core, can be a metal, semiconductor, magnet, catalyst, and so on. And if we just, for the sake of focus, pick one subset where the core is semiconductor, we arrive at a system where we can, like we deal with quantum dots, and quantum dots has been an awardee of a relatively recent Nobel Prize, just less than 2 years ago. And these materials turned out to be extremely powerful, both intellectually and scientifically, but also practical. So they are now used commercially in displays, in TVs. They're used in energy technologies, in bioimaging. They're researched for quantum information science and infrared cameras. So what this made these materials that practical is the ability to kind of bridge the gap between functionalities that have been previously associated with inorganic semiconductors primarily, and on one side, and also structural flexibility and processability that we previously saw mostly in polymers. Now we can do kind of both at the same time. If we dig a little deeper into the chemistry aspects of these material systems, we can think of 3 families of quantum dots based on the chemical nature of the anions in their chemical formulas, chalcogenides, pnictides, and halides. Why I'm showing this example is that it allows us nicely kind of highlight the difference between these materials. So the type of anion will determine the nature of chemical bonding in these materials. So halides will be the most ionic materials, and ionicity of chemical bond means that there is no energy penalty when we change the angle between atoms, or the angle between chemical bonds. And as a result, the ionic materials are ionic bonding is generally very labile, and atoms can efficiently move around. On the opposite side, we have pnictides that are most covalent in this series. And covalency means that we have more rigid bonds, but they are also more difficult to make and more difficult to get out of local traps. However, once you make this material, they will be also the most resilient under external abuses with electric fields, optical fields, and as a result, the materials that are most difficult to make often top the performance metrics. Like, for example, if you look at the current world record solar cells, the upper third of it will be exclusively the world of 3-5 semiconductors. If we think about fastest transistors or the most powerful solid-state lasers, they also all will be made out of gallium arsenide, gallium nitride, and similar 3-5 semiconductors. Only after 30 years and 1 Nobel Prize of very active research and development, the only 3-5 semiconductors that could be made by solution methods, the traditional methods that we used for synthesis of quantum dots, are indium pnictides, indium phosphide, indium arsenide, and indium antimonide. And just if we look, well, just as an example, if we look at the current cross-section of the current world record solar cell, you'll see it will be very different and well matched to each other electronically and structurally, 3-5 semiconductors, but none of these phases have been made by solution methods despite years and years of attempts. Why? So that's mostly related to something that I did not appreciate until recently, the importance of micro-reversibility in crystal growth. So there is, if we talk about any crystal, that is made through some chemical reaction, there is no chemical reaction that can repeat itself Avogadro's number of times without making many, many mistakes. And the only way for these mistakes to kind of not impact the product is when every step can be reversed. So every crystal grows several steps forward, 1 step backward, several steps forward, 1 step backward. And it is chemical selectivity during the backward step that allows crystals to exist. So this reversibility is extremely important, and you see it kind of influencing what we can make and what we wish we could make. And here it's nicely demonstrated. Like if you look at materials that we've been able to make by solution methods for ages, and look at their bond dissociation energy, and materials we wish we could make, but we couldn't by solution methods, there is a clear difference. So material, it is not difficulty with making bonds, it is difficulty with breaking bonds that prevents us from making this material by solution methods. However, sure, we could make gallium arsenide or gallium nitride for many years, and why? Because all these energy scales are referenced to KBT. So it means that if the reaction is irreversible at 200 Celsius, we can go to 500 Celsius and it establishes a reversibility. And that's how this type of problems have been solved in chemical vapor deposition, in molecular beam epitaxy. Now, if we try to do it in solution, we are limited by the temperatures that can be withstand by solvents, surfactants, and all other components of the reaction mixture. And if we think about traditional methodology that relies on using like specialty developed high boiling solvents, the highest temperatures we can probably operate up to is about 400 Celsius, where it is a temperature where carbon-carbon bonds, carbon-hydrogen bonds start falling apart. And that creates a clear kind of gap between parameter space that we can access by solution chemistry, and definitely was very, very successful methodology, heavily developed over 30 years, and the parameters that we know we need to access to make many technologically important materials. And again, after failing many attempts to make these materials. So how can we do it? What can we do to kind of close this gap? And some years ago, we started playing with molten inorganic salts as a possible solvents for doing solution chemistry, or especially colloidal chemistry. But the first prerequisite to think about colloidal chemistry, you need to have colloidal solutions or colloidal stability. And the interesting kind of anecdote here is that prior to this work, nobody looked into colloidal stability in molten salts. And it turned out that these colloids form spontaneously. And I've been asking myself why it has not been discovered 100 years ago, because all ingredients have been around. And probably the most rational explanation is that the very stability of these colloids in molten salts cannot be explained by traditional series of colloidal stabilizations. Like if we talk about colloidal stability in any polar medium, so, well, for colloids, first of all, to exist, you need to have long-range repulsive potential between particles, so that keep particles apart and don't allow them to crash and aggregate and precipitate. So it means you need to have long-range repulsions that will act at the distances larger than van der Waals attraction. Well, in polar solvents, in polarizable media, this repulsive term comes typically as electrostatic double-layer repulsion. You have surfaces, charged surfaces, and they kind of repel each other. However, the range of electrostatic interactions is determined by polarizability, is determined by a parameter called Debye length, which in turn will be determined by the concentration of mobile charges in your solvent. And if we just use kind of numbers from these extremely polarizable molten salts, the Debye length becomes on the order of interatomic distances. So there is no way how these forces can be longer ranged within a traditional framework compared to van der Waals for attraction. However, these colloids do exist. And so what happens here, as we understand it now, it's a very different type of colloidal stabilization. So we have, in traditional colloidal systems, we have relatively low polarizability of the solvent, and as a result, electric field decays exponentially into solution, and this framework based on Debye length is accurate description. However, if we go to much more concentrated electrolytes, we switch to a situation where electric field, instead of decaying exponentially, starts oscillating. It's damped oscillation, which is kind of charge density wave set by the ionic layering templated by the surface charge. And this templating and this layering can propagate for about an order of magnitude beyond the Debye length that establishes these long-range interactions that we need for colloidal stabilization. And I want to use this opportunity to thank Ben Du and Karina Chapman and others who helped us to establish it years ago. And it was a terrific journey, but I now want to move towards better understand like what we can do on the materials design area. And the first type of chemical reactions that we studied or capabilities that we explored was chemical reactions on nanoparticles, like transformations. I told you already that we can make indium phosphide nanocrystals, for example, and they're used in every actually TV that you can buy commercially. It's really well optimized process. And if we start with indium phosphide and put it in a solvent, potassium tetraiodide gallate, it's our liquid, we can drive the reaction where gallium will go inside and indium will go outside, and we can convert material from indium phosphide into indium gallium phosphide. And we can do the same with indium arsenide, converting it into indium gallium arsenide. And that's how first examples of these quantum dots of these important semiconductor phases have been made. If we kind of swipe under the rug 5 years of hard work and kind of I can show you that these type of chemical transformations can be generalized across pretty much the entire family of 3,5 phosphides, arsenides, and antimonides. And of course, the question is, and these materials will look pretty good in terms of their X-ray diffraction data, electron microscopy data, but of course the question is how good these materials electronically. Are they really defect-free and structurally perfect to the degree that we can use them as quantum dots and for all the applications? So it's a very loaded question, and I think it will take many years to optimize each of these materials, but we can start somewhere. And I will show you one example of indium gallium phosphide quantum dots, with a little bit of optimization, you can make materials that show quantum yields on the order of like 50 to 90%, which is very much on par with the best quantum dots we can make by traditional methods for materials that have been optimized for many years. However, an interesting point is that as we add more gallium into the system, at a certain point, photoluminescence from being nearly perfect just suddenly drops to 0. And that actually very nice can be nicely explained if we look into the band diagrams of parent bulk phases. So we have a transition from direct to indirect gaps that we can analyze both spectroscopically and computationally. Now, the important point here is that the very idea of band diagrams relies on using momentum, crystal momentum, as a good conserved quantum number, which relies on perfect lattice periodicity. So it has been a big discussion, and is a big discussion in our community, like how to think about quantum dots in each particular case. Is it periodic? Is it not periodic? So like for single exciton processes, availability of this material allowed us to clearly demonstrate that momentum is conserved. For multi-exciton processes, it's not conserved at all. So it's just an interesting handle for spectroscopic studies, but also it can be surprisingly practical. Like I'm sure some of you have QLED TVs at home. It's now like a big technology, but industry is now moving towards next generation quantum dot displays that are based on electroluminescent device stack. And the problem is that we have red emitting pixels, green emitting pixels, very well optimized, very stable, and we are badly struggling, or industry badly struggles with blue emitting pixels in terms of stability. Current material is tellurium doped zinc selenide, and it has been optimized for many years with very limited progress to the best of my knowledge, and we work closely with industry. I think I have access to this information. Now, if you think about alternatives, we don't have many options that are cadmium-free, that are well behaving, and we have the only other system that emerges as a possible alternative candidate is indium gallium phosphide, where we can use this molten salt exchange reactions and develop materials that emit perfectly in the spectral range of blue subpixels. Now, if we so these materials show pretty good and promising performance characteristics, and we are currently working with Samsung exploring them for LEDs. Let's see how far it will go. But moving forward in terms of synthetic methodology, so far I've been showing you chemical transformations on pre-made nanoparticles. The big question for us and milestone was, can we make materials? Can we grow heterostructures in molten salts? And surprisingly, the answer is yes, and surprisingly in the way how kind of well it worked, and a lot of science that has been originally developed for organic solvents turned out to be transferable and applicable to molten salts. There is kind of a lot of kinetic problems or kinetic phenomena that can be transferred, and nucleation and growth occur surprisingly similar in molten salts to organic solvents. And yeah, so that was relatively recent work and example of like first gallium arsenide quantum dots grown in solutions showing emissive properties, size-dependent properties. But again, I think it's an important milestone, but and it's important development that allowed us to put 3-5 quantum dots now, solution methods for synthesis of quantum dots on the map. And actually a lot of this work now, all these phases now can be made using colloidal chemistry in molten salts. But actually at the same time we already keep moving further towards the next frontier, another challenge. And I think we have a lot of excitement these days about attempting to make nitrides. Because in many ways, nitrides like gallium nitride, indium gallium nitride, aluminum nitride, look from the photophysics perspective, from stability perspective, sustainability perspective, like ideal quantum dots. The problem is that like from CVD community, we know that for gallium arsenide, we need to run the reactions at around like 600 to 700 Celsius. And it was quite a journey to go from here to here. For nitrides, we need to go typically to 1000, or that's where CVD reactions are carried out. And that turned out to be difficult for a number of reasons. But we learned that actually all bulk gallium nitride crystals grown on this planet commercially are grown in supercritical ammonia. So it's high pressure allows you to establish micro-reversibility under lower temperatures, and that prompts us to develop a whole different infrastructure and pretty unique infrastructure for high temperature, high pressure colloidal synthesis in molten salts. And to show you our latest development, let me put it in perspective using the ammonia phase diagram. So it's ammonia phase diagram, so we have ammonium gas, ammonium liquid, supercritical ammonium, triple point. And well, that's where traditional colloidal synthesis operates. That's where organic is falling apart. That's where CVD and MBE community operates. That's where ammonothermal synthesis, supercritical ammonia synthesis for bulk nitride growth operates. And in the middle of this phase space, there is a sweet spot where colloidal nitrides in molten salts can be just formed spontaneously. To kind of show you what happens as we kind of take a crosscut through this phase diagram, if we, for example, at around 500 Celsius, below this sweet spot we have aggregated garbage. Above this sweet spot we have larger crystallites, and somewhere in the middle we have like pretty nice colloidal nanocrystals. And what is a bit kind of mind-blowing is that it's very generalizable. It's surprisingly universal. So it works like for different transition metal nitrides, for gallium nitride, for niobium nitride, tantalum nitride, and these are important materials. Titanium nitride is known for its plasmonic properties. Vanadium nitride is used in energy storage. Gallium nitride in lighting. and power electronics, niobium nitride is an important semiconductor, catalyst, and so on. And all these materials can be accessed using molten salt high pressure ammonia synthesis and recovered in form of colloidal solutions in different solvents. Now, what is going on? Like, why? What is the origin of this sweet spot? My current understanding is that it comes from the surface structure and surface terminations. Like, if you run this reaction at about ambient pressure, the particles, as soon as they nucleate, they aggregate, because they are terminated by non-polar 100 type facets, and under these conditions they are easy to undergo so-called oriented attachment or sintering, while as we increase the ammonia pressure, you reconstruct surfaces and they become primarily nitrogen terminated, even non-polar surfaces, and that's what we see in ab initio molecular dynamics models and so on. And these surfaces are much more resilient to sintering and oriented attachment. Particles nucleate and grow, and you can recover them in form of colloidal solutions. Now, why is it important? Actually, we see kind of the same pictures that we previously discovered for gallium arsenide. So you need to have high temperature to make high quality and emissive gallium nitride quantum dots. So like, and it's, again, you can find such evidences in the prior CVD literature. They grow gallium nitride at 1000 Celsius for a good reason. Because whenever materials are grown at lower temperatures, you see this famous, they're called yellow band, that emerges due to point defects, particularly gallium vacancies or carbon sitting on nitrogen sublattice. But as soon as you go to higher temperatures, in CVD, in thin film, you need to go to 1000. In quantum dots, it looks like you need to go to about above 520 Celsius. You see disappearance of this trapped emission and appearance of band edge emission. And that turned out to be pretty important, and you can see also it always coincides with emergence of nice kind of textbook Raman spectra of the material. So it's actually Raman is probably the most telling and insightful analysis tool for 3-5 semiconductors, colloidal 3-5 semiconductors, far beyond traditional methods like X-ray diffraction or electron microscopy. Well, yeah, so that's kind of taught us that if there was no progress for many years, you sometimes should think outside the box. And now let me kind of switch gears. And so far I've been talking about nanoparticles, where we kind of developed a new core, new ways to make core, and now it can be combined with a very established and mature field, how we can design their surfaces and organic part. So here we kind of inverse the story. I will talk about a case where kind of the core, inorganic core, has been mature, but we developed surface science. And that will be related to a whole new class of materials, two-dimensional transition metal carbides and nitrides called magazines. And they are, I'm really mind blown by kind of chemical richness of these materials. So they are early transition metals of many different, early transition metals or lanthanides and actinides made in form of carbides, where you can have selectively and precisely make phases where two layers of transition metal are bonded together through carbon, layer of carbon, 3 layers are bonded through 2 layers of carbon, 4 layers of metal, 5 layers of metal. They can be made in form of monometallic, where you have only one transition metal. You have solid solutions, ordered intermetallics, high entropy, like up to now 9 transition metals. So it's an extremely rich space where you can design all kinds of composition and structures, and This material, this is one of the newest, maybe the newest family in organic materials, flatland, discovered at Drexel University in 2011, but now probably the richest already. But that's just part of the inorganic core part. If you think about traditional two-dimensional materials like graphene, molybdenum disulfide, they don't have surface signs. Magazines do. We can do all kinds of surface reactions, and by exchanging these atoms bonded to surface to surface layer in form of inorganic, organic, and most recently organometallic. So these are truly interfacial materials where we can use all the tool set from inorganic chemistry, organometallic chemistry, where to engineer surface groups, redox atoms, we can use electrochemistry because these materials are metallic, so we can control their surface potentials, we can control intercalation and the intercalation of ions between the layers and stacks. And I will show you a few examples. First, let me tell you how these materials are made, and that's, again, has been discovered around 2011. Again, to establish microreversibility, we need to, in materials with very strong bonding, we need to go to some very unearthly conditions. And this is established by using solid-state chemistry. So you react titanium, aluminum, and graphite at about 1500 Celsius, forming max phase, which is just a ceramic. And if you take this ceramic and put it in aqueous HF solution, for example, hydrofluoric acid, it will etch away the layers of aluminum selectively. And what looked like a normal crystal falls apart into this stack of leaflets with atomic precision, and that can be delaminated, exfoliated, and as you can see, these materials are very, well, it's a very scalable approach. Problem with this approach is, of course, HF wastes and other things, but if we talk about chemistry, the problem is that at the surface, after this etching, you have a mixture of hydroxo, oxo, and fluoro terminations. Okay, I will explain why it is a problem. More recently, another methods have emerged, and we contributed to it quite a bit, based on using molten salts, where you can etch max phases into magazines at molten salt, where now the surface terminations are chlorides or bromides. Why do we care? Because if we want to do surface chemistry, if we want to do surface exchanges on these groups, to make a new chemical bond, you need to first break a chemical bond that existed previously. And titanium oxygen, titanium fluoride bonds are extraordinarily strong chemical bonds. So this is thermodynamic sink that you cannot modify. But on the other hand, chlorides, and again, we can look at the bond dissociation energies, or bromides, are much weaker bonds, more labile bonds, and we can play with them, we can change them. And we have shown a few years ago that indeed, if we make this chloro-bromo-terminated magazines through molten salt etching approaches, you can then do anything with these materials. You can do chemical modifications, you can do nucleophilic substitutions, you can do reductive elimination. So all this classical textbook inorganic chemistry, but now that typically people do with molecules, but now we can do on these two-dimensional materials, and this is cross-section. So this is how each of these layers looks like, that we can later separate if we want, and use in solution. And that kind of creates all kinds of crazy things. So like in case of titanium carbide, it's a very hard ceramic, very brittle, very hard. But if you put these different surface groups, and especially bulky surface groups, they apply steric stress in plane strain, and as a result, the titanium carbide starts acting like a rubber band. You can stretch it by 18%, and that completely changes materials properties. So like surface chemistry can really impart bulk properties of the material. The same magazine, depending on what surface group we put on it, can be bent, can be insulator, normal metal, superconductor, and it's just an example of a surface chemistry completely determines materials properties just because we can change lattice parameters, we can change electron phonon coupling and many other things. Later, next, after we realized how to do these inorganic substitutions, we developed methods for putting organic groups at the surfaces. And just if we again start with this chloride or bromide terminated MAXenes and reacted with pretty much any deprotonated amine, organic amine, you will install organic groups in form of, like if those are N-alkylamines, it will be bilayers of self-assembled monolayers kind of inserted between inorganic sheets. We can do much more elaborate structures, but what is really mind-blowing, and we are still working to understand mechanistic aspects of it, how these huge molecules can crawl into this small space fully topotactically without disturbing any crystalline structure. So just this stack swells like about almost an order of magnitude kind of in thickness. And these chemistries allow us to engineer the interlayer spacing. So you can insert different molecules with different nucleophilicity, with different polarity or reducing or acidic environment and so on. And it allows us to really engineer environment inside these stacks that is very different from environment outside, which is instrumental for designing interesting chemistries. So like most recently, the work that is currently in progress, we started looking into catalytic properties, because early transition metals are known for their very rich catalytic chemistry. And even with like traditional, relatively well-known and traditional hydroamination reactions, we saw a completely new reactivity where the leaving groups is acetylene and again, when coupled to microenvironments, it allows us to look in different ways into catalysis, catalytic properties, and catalyst design that is neither heterogeneous nor homogeneous. So we create microenvironments kind of building around ideas, borrowing ideas from enzyme chemistry where you engineer binding pocket around the catalytic center. So this kind of interesting work in progress enabled by all this surface chemistry of MAXenes. Even most recently, we have demonstrated that this type of chemistry actually that was originally developed for MAXenes is much broader. There are hundreds of phases of two-dimensional materials that have relatively strong and directional covalent bonding, in-plane bonding.
Emergency notification system. This is a test.
Thank you. So, and you can do other substitution reaction. If you have strong in-plane bonding and labiles, like typically metal halide out-of-plane bonding, you can do similar surface reactions as we discussed. So, and you can make, like MAXenes are metals. Now we can do it on semiconducting two-dimensional materials, other materials. So magnetic is interesting magnetic orders. It's much more rich in universal chemistry where we can take a two-dimensional sheet of two-dimensional material and turn it into a whole family or using different inorganic and organic chemical substitutions. Okay, so I think now it's time for me to finish. I just want to leave with making a statement that MAXenes are a chemist treasure trove. They are pretty unique in terms of chemical diversity, engineerability, sustainability, scalability, and ability to really kind of play with it, how an extremely rich parameter space here. But now let me use this opportunity to thank my research group and who did all this work, the funding agencies that kept us afloat over the many years that we played in this space. And also I want to thank collaborators, especially people here at APS and CNM whom we worked with for many years and who just made a lot of this work possible. Thank you.
Thank you, Dimitri, and thanks for helping us keep on time, too. You cut your talk a little short there. I actually was trying a lot of those 3-5s. I just thought if I added the right ligand to a nuclide that it would make the greatest quantum dot ever, and it never worked. So much unpublished data went into that. I am curious, okay, this is kind of a silly question, but when you make these in these salts, how do you get them out, process them for subsequent transformation, specifically the subsequent shelling?
Oh, absolutely. So it's the way we do it is after synthesis, we synthesize in molten salt. Like, for example, this is our solvent. After cooling, we dissolve molten salt in a solvent like typically DMF or acetonitrile, and it just dissolves. So the quantum dots made in molten salt can be isolated collected as a powder, and then you put organic ligands. And in this case, it is a colloidal solution in toluene of gallium arsenide quantum dots with oleoamine ligands. So now we can plug into or use all the methodologies that we've been optimizing for 30 years. Of course, the next question you may ask probably scaling. How scalable is that? And that's, well, we can, it's still kind of work in progress, but my understanding is that we can go to pretty high loading concentrations, especially for cation exchange reactions, up to 10% of the concentration, like mass ratio of quantum dots can be used and treated in molten salts. So it's just to make a kilogram of indium gallium phosphide quantum dots, we may need like a couple tens of kilograms of total solution, which is probably reasonable.
Thank you for the wonderful talk. I have a question about the indium gallium phosphide with the X value. Why it shows, like probably the previous slide, it shows a very different quantum yield. Could you please explain that a little bit? Thank you.
Yeah. So what is happening is that when you have, well, let's look first in the parent phases. Indium phosphide is a direct gap semiconductor with a bottom of conduction band in the gamma point of the Brillouin zone. Gallium phosphide is indirect with the bottom of conduction band in the X valley. As you start alloying these materials, this valley moves up and gamma valley moves up, X valley moves down. At some point they cross. And the state that comes from like excitonic state, like 1s quantum confined orbitals in the conduction band, in indium-rich region is originating from the gamma valley, but then in gallium-rich region, there is a crossover and it originates now from the X valley. So of course, gamma valley, X valley, K, it's all language of bulk semiconductors. And it works perfectly only for perfect crystals where you have infinite periodicity. So here we have periodicity over about 10 lattice periods. Which of these physics kind of captured still, which is not, is an open question and turned out to be, needs to be dealt with for each class of problems individually. For single exciton behavior, I think it's, yeah, so the K is conserved, so and states are originating from the X valley are very dark compared to states originating from the gamma valley. For biexcitons, not at all. But the beauty of this system is that for the first time we had a material where we can kind of systematically drive it through the crossover from direct band gap quantum dot to indirect band gap quantum dot. And that has not been possible before.
Go ahead and I want to introduce our next speaker, Ephraim Rodriguez. Am I saying that correctly? From University of Maryland.
Ephraim, yeah. Ephraim. Thanks. All right. Well, first of all, thanks so much for the invitation. I've really enjoyed all the talks and look forward to the workshops and also the poster session this afternoon. What I want to talk about also is continuing this theme of synthesis. And here you see a diffraction pattern contour plot of data from 17BM taken here at APS. And I want to talk a little bit about what we can learn from peering into the so-called black box, which is a term that Karina Chapman used yesterday. So my interests are in quantum materials, and so there are two reports from Basic Energy Sciences. One came out not so long ago, well, it's going to actually 9 years ago. And it was trying to define, what quantum material is, and in some ways it's just a catch-all umbrella term for a variety of materials like sign correlated electrons, topological, sometimes even multiferroics, and definitely superconductors, which is one of the areas that I'm really interested in. They're also like quantum spin liquids, of course. And another interesting report by the Basic Research Needs is on synthesis science. So we're very much interested in quantum materials, but how do we discover new ones? And so there's some quotes here from this report. Not only must we know how to make and design a material, but we actually have to be able to make it as we envision it, and that we have to think about ways of approaching the science of synthesis, not just synthesis on its own, and to try to understand how to get the atoms to where they need to be, not just where we want them, not just predictive, but also actually the kinetics of getting there. So these are my two interests. These are two papers that I also found very interesting. Synthesis of metastable inorganic solids, and makes a good point that the number of known inorganic compounds is dramatically less than the predicted due to these synthetic challenges. And so a mechanism approach to inorganic solid-state chemistry is sort of the holy grail in this field at the moment. Another interesting paper, again with Karina's here, is on the predictive synthesis of inorganic materials. It remains a grand challenge in material science. And so that's something that really motivates me. And so what we do at Maryland is think about quantum material synthesis. We actually have, I'm going to just plug in this school, we have a winter school that we've been running since 2017 and funded by NSF and Moore Foundation and ICAM. And we even have now a little textbook that we've come out with to go with the winter school. And it's one of the unique schools that actually we really focus in on synthesis and crystal growth. So the students come in, we have pedagogical talks, and then in the afternoon they go into the laboratory and actually do some synthesis, crystal growth preparation. So if you're interested in this, please send your students or have them apply. We fund their stay and also their travel. Our approach is actually to grow large single crystals. Most of that motivation is because a lot of times with these quantum materials, you want to be able to do bulk property measurements, whether it's transport, heat capacity, or let's say neutron scattering, which requires a lot of material. So we really try to focus in on that. These are just some representative crystal structures or crystals that we grow in our lab, from metal oxides or phosphates to a lot of selenides, sulfides, and thiophosphates. And our approach is to really use anything that we can in the lab to get to the right crystal growth conditions. And so that includes a combination of chemical vapor transport, hydrothermal synthesis, solvothermal synthesis, molten fluxes, salt metathesis reactions, and so forth in order to get there. And so today, that's what I'm going to present on, is on the synthesis of hydrothermal, solvothermal, and the so-called salt metathesis. Several of the speakers have really done a great job introducing the world of van der Waals materials, sometimes called 2D materials. And we just saw the really awesome talk on Maxine's. And for us, what's really nice about 2D materials is that they allow for intercalation chemistry, we just heard about, As a solid-state chemist, many times we're taught, one way to affect the functional property is by doing like cation substitution, right? Allovalent or isovalent substitution, known in high TC superconductors, manganites, and so forth. And that's very true for three-dimensional metal oxide type materials. But what I really like about 2D and van der Waals materials is you got one more vehicle there, which is to insert molecules in between the layers, and you can do charge doping that way, or you could modulate the spacing between the layers. So there are new sort of knobs that you can turn in when it comes to 2D materials that you may not have access to in three-dimensional materials. So the ones that I'm really interested in are these transition metal chalcogenides, transition metal chalcophosphates, and TMDs. I'll just be talking about the top two today. So part one is about the intercalation chemistry of iron-based superconductors, and specifically iron selenide. In this case, I'll say something about iron sulfide though as well. And these sort of interesting kind of twisting that you can get in some of these layered materials. And then the second part will be about van der Waals materials that are chalcophosphates. And this is just a contour plot of some data taken here at the APS, some diffraction data. And we're trying to make these materials that are either mod insulators or are ferroelectrics or multiferroics. So they're very interesting. The second part is not so much on the intercalation chemistry, but really the substitutional chemistry you can do within the metal sites. Okay, let's get started on the superconducting part. So motivating us, of course, is that superconductors have a wide variety of potential applications, whether they're used to establish large magnetic fields that are used in MRI as an example, perhaps in transportation or transport. And one of the latest ones, of course, is coming up with superconducting quantum bits or qubits, such as the IBM model here, where you can potentially use superconductors in this application. So for us, we're motivated to actually, as chemists, as solid-state chemists, to make materials that are going to be, that have the critical temperatures at elevated temperature, such as liquid nitrogen. That would be something that we're really interested in. And I think that iron-based superconductors actually offer a very interesting vehicle towards getting there. So I was motivated by looking at some of the older literature, for example, the literature by, the papers by Frank DeSalvo in the early 70s, where he was intercalating these really large molecules in between something like tantalum disulfide, these stereoamides, that are actually like 50 angstroms long, and you can actually make this material more two-dimensional by doing so and raise the TC. However, the TC raises by like maybe 2 Kelvin or 3 Kelvin, it's not huge, but in the case of iron-based superconductors, FeSe in its tetragonal form is 8 Kelvin, and as Simon Clark demonstrated in this paper, as soon as you insert ammonia molecules with lithium, you raise it all the way to 43 Kelvin. So it's quite drastic change there. And so what we've been doing in my group is making these sulfides and selenides, mostly selenides if we want a good superconductor. Sulfides can also be superconducting, but they have lower TCs. They're good though to start out with from a synthetic point of view, mostly because it's cheaper, like thiourea as a reagent or other sulfur-based reagents than selenium ones. But in any case, you can see, you can make just these layered ones with nothing in between. You can insert alkali metals. Sometimes that can lead to instabilities within the layer, and you cause vacancies, for example, which is bad for superconductivity. And then I'll say something about these ethylene diamine intercalated ones and hydroxide ones as well. If you're not familiar with the iron-based superconductors, let me just say something about their basic structure. The iron is always coordinated tetrahedrally, and the metal sublattice fundamentally is a square sublattice, okay? And I just contrast that with something much well studied, like transition metal dichalcogenides, where the metal sublattice is typically a hexagonal one. Even though we have polytypism, of course, in TMDs, Fundamentally, it's a hexagonal lattice for the d orbitals, how they are arranged. And the d orbitals are of primary interest to us because those are going, what we call the frontier orbitals at the Fermi level of these materials. So coming now to APS, what we like to do is a lot of in situ studies. This is an example of what we do here at 17BM a lot. We, for example, will take materials and put them in this environment with furnace elements. Sometimes we want to actually test it under different environments like methane or hydrogen, inert or oxygen. But in this case, what we're doing is synthesis. And so we thought, okay, why don't we try looking at how we make these materials hydrothermally and solvothermally. When you do hydrothermal synthesis, you place your reagents in water and in a Teflon cup that goes into a stainless steel autoclave. You put it in the oven and you hope that you're going to get your product, right? And you don't know exactly how much time the reaction should go for, when it's complete. You're waiting for the whole PAR bomb apparatus to come to thermal equilibrium with the oven and so forth. I like to say hydrothermal synthesis is kind of like pressure cooking because you're trying to get above the boiling point of water and above 1 bar of pressure. But nevertheless, we're trying to always figure out the parameters that are going to lead to a high TC superconductor, for example. So we thought, why don't we come to the APS and actually do it in situ? And so 17BM was one of the beamlines that we really did a lot of this work at. This is my student, Huafei, and this is just a snapshot of, where we oscillate as we hit the tube. We actually could just get away with simple quartz tubes. We pressurize with about 7 atmospheres of pressure. This is what we call gentle or soft hydrothermal. It's 120 degrees Celsius, so it's not super high. And then you don't need to go very high for making these materials. Solvothermally, we have sort of similar conditions. We go slightly higher. Each sequence is 3 minutes. We collect thousands of powder patterns, and then we do quantitative analysis with those, or Rietveld analysis. So solvothermally, you just replace water with any other solvent. In this case, we use usually ethylene diamine or other amines. You try to have a solvent that has similar viscosity to water. In some ways, hydrothermal solvothermal synthesis depends on mass transport. And so you have some kind of temperature gradient. And as the previous speaker was talking about this sort of reversibility in crystal growth, you try to also have this sort of reversibility or be close to equilibrium if you want to grow large crystals. This is an example of a contour plot showing the thousands of powder patterns. We start out actually with iron metal and thiourea. Again, sulfur is the easy test ground instead of selenium. And you can see we fit the data, it's just iron metal. And then the metal oxidizes in H2O, and you evolve iron 2+ in solution. And then the iron 2+ reacts with SH- anions in solution, and now precipitates out the iron sulfide layers. So if you do it with lithium hydroxide, you get this lithium hydroxide layer intercalated between iron sulfide. If you do guanidine breaks down and you get ammonia that actually intercalates with protons inside the iron sulfide. If you do it with ethylene diamine or solvothermally, you get these ethylene diamine coordinated complexes that go in between your iron layers. And so this is just an example of how that evolves. You can see how much time it takes, about 20 hours or so. And then this is a Rietveld analysis of our product. And what we get is also the byproduct, like lithium carbonate, for example, in this case. So this was a targeted product here. What we find out actually from doing this Rietveld analysis, and actually I should say shout out to Brian Toby and Bob Von Driel who developed GSAS2. here at APS, and it's been really, really useful in doing these sequential refinements of these thousands of powder patterns. What we have here is just how the iron gets consumed with time, and then we can see the lithium hydroxide iron, the target compound here. So sometimes we do hydrothermal reactions, and you read in literature like, 7 days in the furnace or oven. And actually, you can see you don't need 7 days. This can be all done within half a day, right? And this is just showing the volume, the lattice volume, as we refine it. And it was interesting to note like this little blip here in the volume expansion. What we can also do with quantitative analysis is actually look at the iron concentration in the lithium hydroxide site. And that's actually a very important point for superconductors, because for these iron selenides and sulfides, what happens is you have some charge transfer from the hydroxide into the selenide or sulfide layer. That's the charge doping part that raises the critical temperature. And the question is, well, how much? How much should be in there to make an optimal superconductor? And what we found from the synchrotron refinement or the powder patterns is that actually this is the sweet spot right there. At about 200 minutes, you populate with about 20 to 15 to 18 to 20%, let's say, iron in there. It's iron 2+ substituting in for lithium 1+, and so you're basically putting in 0.2 electrons into the iron sulfide layer, and that's your optimal superconductor. As you can see, it actually is pretty dynamic, and it diffuses out of that layer and back into solution. And that's why many times for hydrothermal synthesis, you get irreproducibility in your results. You think that you've made it structurally from laboratory x-rays, it looks good, phase pure, you put it in the magnetometer, then do susceptibility, not a superconductor. And so I think it's very nice to see how synchrotron radiation, synchrotron source powder patterns at 11 BM allow us to do, 17 BM rather, allow us to do this. And so we've come up with a scheme about how to both insert lithium hydroxide or other metal hydroxides to understand, have better control in making these kinds of materials. Now, how can we get higher than 43 Kelvin? This is at least a dream of mine, is getting to liquid nitrogen. I showed you our results on the lithium hydroxide with some iron substitution there. But what's very intriguing is that there have been some studies where iron selenide gets exfoliated to the single layer limit, placed on a strontium titanate substrate, and TC can be above 65 Kelvin. Now, can that be reproduced with bulk crystals and measured with resistivity and magnetic susceptibility and so forth, all the sort of tools that we have? And so I was thinking, well, what makes it special? Perhaps it's the fact that you can strain the iron selenide lattice when you do that on the substrate. So we thought, let's make what's called a mismatch layered heterostructured material. And so we want our iron selenide layers, which again have to accept some electron charge to become a high TC. And then what we can do is use something called a layered double hydroxide, which is not based on a square lattice, but rather hexagonal lattice. And so we thought if we're trying to sort of force a hexagonal lattice into a square lattice, that could potentially strain the iron selenide. And what's cool also is these layered double hydroxides are cationic layers by nature. So they intercalate all kinds of anionic species. So they should be able to transfer some electrons over to make the iron selenide negatively charged. Another interesting thing about them is how tunable they are. You can put magnesium, aluminum, or any other divalent, trivalent cation that's not too far off in the radius size. So, and actually, we got the idea from nature. There's a mineral called tashilinite that's iron sulfide based, and you see these kind of nice whisker crystals. And it's no surprise, I guess, because hydrothermal is a way to make minerals or to dissolve minerals. So if we're trying to make something like a superconducting mineral, it's kind of the natural place to go. So we haven't, so we found it in the 17 BM powder patterns that we could make that phase. Then we went back into the lab, and then we actually scaled it up and made some of these materials, and we're able to make several of these. One actually really interesting thing that we also found out is that if you do this in D2O as opposed to water, you minimize how many iron oxide impurities you make. And the reason we were trying to just deuterate the sample is for one of the reasons I was telling you about earlier about neutron diffraction being isotope specific here. It turns out that deuterium has a very different incoherent and coherent cross-sections from hydrogen, and so we were just trying to minimize hydrogen background and neutron diffraction. Nevertheless, we were able to make these materials nicely and so forth. So you can see actually that they do sort of strain the lattice a little bit, and we're able to make all these, this is from electron diffraction patterns, to make these super lattices as we do these mismatched layered materials. So I'm going to come to the next point, which is actually, so we haven't yet raised the TC higher than 43 Kelvin in these, and a lot of it has to do with the fact that there's some kind of charge imbalance I can go into later, but in the interest of time, I'm going to say something about intercalating other species in between here, like ethylene diamine. One of the things that we found out is that there's another degree of freedom here with layered materials, and that is that they can twist. And we didn't really expect that until we started seeing the diffraction patterns. And so, in fact, what we have is something interesting called the coincident site superlattice, and they can occur between materials that have like a really high symmetry, like hexagonal or fourfold symmetry. And what happens is one layer tries to match with the next layer, and it makes a superlattice in the process from twisting, and you have very like set angles that you can get. And we found several superlattices that we can get, so we can index them. And actually the crystallography on this was not too terrible, because you could just use an index having to deal with the zone axis that you're looking down. And this angle that you can get is just the arctangent of 1 over some index, and you can make prescribed twisting angles when you do the solvothermal syntheses of these materials. So what's cool about that is we're trying, right now it's a central symmetric material, but we think that if you tune the right solvothermal synthesis, you could potentially break inversion symmetry and get like maybe a chiral material. In this case, it's not chiral. It actually one layer twists in one way, and then the next layer twists back, so you end up recovering inversion symmetry. But it's a very interesting idea. We actually did it for cobalt. We also put this on the beamline here. This is actually a single crystal structure, and we found that it does break inversion symmetry. In this case, it actually makes a polar space group in this way. And this is again 17 BM data. We can see we put cobalt, thiourea, ammonium chloride, as we call a mineralizer, in ethylene diamine, and we form these compounds very nicely. So you can see how they form. Actually, the solvothermal is a little bit different from hydrothermal. It's more sluggish. You generate a lot of side products as well that we didn't in the hydrothermal. For example, we make these salts of cobalt ethylene diamine with chloride in there. And so it's a little bit tougher, and that's why I think it makes sense that it was harder to get some single crystals of these materials. But at least that we know, what we're looking for now, and what sort of how we can tune the solvothermal conditions to try to avoid some of those side products. It's very similar to the hydrothermal, though. We start out with native cobalt metal, and then it slowly oxidizes in solution. It's actually an interesting compound. It's polar because those ethylene diamine molecules hydrogen bond to one of the layers, and that breaks the inversion symmetry. So it's an example of a polar ferromagnetic metal. So I wouldn't call it a ferroelectric metal, because that doesn't make any sense, but indeed it's a polar space group, it's metallic, and it has a ferromagnetic transition at 43 Kelvin. So this one's not a superconductor, but instead a ferromagnet, which is interesting because when you go from iron to cobalt, it's a 1 electron change when you do that. So to summarize this part, what time did I start again? I forgot what time it started. 10 minutes later, so you have till 11:05. 1105, okay. Summarize this part. From this, from all this data, we're sort of now very much motivated to see, like, how can we make non-central symmetric quantum materials where we either can break inversion symmetry by making it chiral or by making it polar. And I think doing it salvos-thermally, where you insert these molecules in there, is a potential way to do that. So, well, as I said, either twisting or bending those layers. And then future direction is to keep tuning these hydrothermal reactions to make these LDH iron selenide heterostructures, these mismatch structures, and see, can we go beyond 42 Kelvin in these cases? And so I'm still very much, after high temperature superconductors, I feel like once you work in that field, you can never really leave it. So moving on to the next part, is chalcophosphates. Let me show you what these materials look like. You can grow crystals with nice lateral dimensions, you can exfoliate them, and what they consist of is basically you have these P2S6 anionic units, and they form these layers, and in the octahedral interstitial position you get metals. So if you just look at the metals, you have a honeycomb lattice that's the basis there. So they're very interesting, and you can make, you can put a lot of different transition metals in there. They tend to be antiferromagnets, but they're also understood to be Mott insulators. So they exhibit some strongly correlated electron behavior. And so, you know, if you want a van der Waals Mott insulator, these are actually good platforms for doing that. And we haven't gotten into doing intercalation chemistry on these yet. We're just starting to explore, like, just making them, how do we go with crystals and so forth. It's interesting looking at the literature, some of these, like in the solid state reactions, there have been reports that it's a 90-day reaction to get out crystals, which is, you know, maybe someone just took off for the, you know, summer and left it there or something. But it is indeed real report. 19 days, make a powder. So we thought, oh, you know, can there be kind of different ways to approach these if some of these are very slow to make? And what we were thinking about is, you know, what about kinetic control as opposed to thermodynamic control? And, you know, something, a topic that's come up already in this meeting. And we were thinking, you know, if you look at the energy landscape in this cartoon, many times you get the you're looking at the thermodynamic product, but if, you know, we raise say the activation barrier and start moving that energy landscape a bit by just lowering the temperature, let's say, or thinking about the reagents that we're using in the solid state reaction, could we get kinetic control? And so, so Karina, you talked about the salt metathesis, reactions. So we thought about doing just the same. We start out with magnesium thiophosphate, which is already in the structure we want. And then we're going to react with a variety of metal salts. Turned out that cobalt chloride was the cleanest one that we used. And then you get this structure, which is, so it's isostructural to the magnesium thiophosphate, and you end up with your cobalt thiophosphate. And then you just wash the side product. So it's nice, and you can see these are just ex situ diffraction patterns before the reaction, after the reaction, and then after washing. So you can make these pretty phase pure. So we came over here again, 17 BM, and we did the salt metathesis reaction. So you see we have cobalt chloride here with magnesium thiophosphate, and then you end up with your cobalt thiophosphate and magnesium chloride, a little bit of cobalt sulfide impurity that we caught. And so these are just contour plots. It's my student Sain who comes and does these. And then we follow, again, using Rietveld analysis, we follow how these, the phase fractions of these proceed. And the one thing that we found out is that actually there's a characteristic temperature we call TD, at which point it's very diffuse scattering you see here, but you start actually forming the new phase. Even though it hasn't crystallized, you can see that it's there. And then at some point, the cobalt chloride melts at like about 480, and then you form a more crystalline form of this cobalt thiophosphate here. So So there are two regimes, one where we call a diffusion one, and then sort of a melting one. And so let me just get to those results here. We do the phase fraction. And so after seeing your talk yesterday, now I'm worried about how much we pack these reagents together. But you can see actually we get to about 60% here, and so the other phase fractions there. So actually it starts to finish at about half an hour. All right, so not 90 days. You actually form well, we're not growing crystals necessarily here, of course, but actually the reaction's pretty fast. You get to your products pretty easily. If that's 425, and then here it's at 475. Once you go higher temperature, it's harder to get those first minutes, of course, in the synchrotron because it's already, the reaction's already going. But we did try to do some fits, some isotherms for the different temperatures to see if we could just do a plot to get sort of an activation barrier to understand what that is here. And it's about 140 kilojoules per mole. And we think it's because magnesium is particularly mobile in these magnesium thiophosphates, and it's able to really come out of the material quite easily. And so this is again that same plot I was showing you. We do find this is a refinement of the C-axis for the product, and it's very noisy. Of course, we have a huge error bar. That's just because at the very beginning, there's not a lot of it there. But we do see it here, and then we see how it progresses, and then at the melting point, you see a lot more of it, so you get a better fit. But nevertheless, it seems like the thiophosphate anion is sort of stretched out in the beginning, and it helps those cations move and diffuse through, and then at some point, it actually closes up in here and makes a cobalt thiophosphate. So this is just a schematic of what we're trying to do. Like at some temperature regime, you're under kinetic control, and really it's about diffusion in and out of these thiophosphates. It's slow, but you could form the product, I guess, if you waited long enough. And then thermodynamic control, actually, it turns out to be pretty good in this instance, even though some calculations from one of my colleagues show that cobalt phosphide and cobalt sulfide are more thermodynamically stable products at this temperature regime. For some reason, we're still able to form the cobalt thiophosphate phase pure. So even though theory shows that it shouldn't be possible, we always actually make this product here. Just in the last, I guess, 5 minutes, where do we go from here? This is one of my theory colleagues. There are other things that you can put in besides cobalt into these thiophosphates. Here's a really interesting example of putting in copper and indium, copper 1+, indium 3+, and so they charge balance. And this is actually a room temperature ferroelectric material. It's a van der Waals ferroelectric material, so it's very interesting. It breaks inversion symmetry because of the way the copper displaces from the octahedral position to the trigonal phase on this here. And just in the interest of time, so maybe we can get some questions in. What we've done is do some data mining in the ICSD to look for new materials. And so we're able to look for all these structure types just by putting in the stoichiometry we wanted. And then we found all the structure types that stoichiometrically match, but we don't want them. These are the ones that are not van der Waals type materials. And it turns out if you put in other parameters like the differences on valence electrons, the radii, and so forth, you're actually able to find material. The open dots are the unknown materials, but predicted. And then the colorful blue circle ones are the ones we want, and triangles are the ones we don't want. And so we're able to now figure out that we want these 83 new compounds that have been predicted in these thiophosphates and selenophosphates. And now I guess it's our job to start synthesizing some of these. And we've made this copper bismuth one now, copper antimony. But it's very interesting to work with my DFT colleague who was able to make all these predictions. And it seems actually it's a very rich playground with these seleno and thiophosphates to make new compounds. And so to end now, I just want to say that in situ reactions on the beamline, they're very useful. We've learned a lot from them. We are able to go down in lower temperatures to understand how these thiophosphates form. And also theory has been very useful in guiding us to making new materials. Let me end by acknowledging my collaborators and also the NSF and the DOE. They funded both these projects. And I want to actually acknowledge also, it's very important that my students come out to APS and also to the SNS. Not only do we get great data, but they also interact a lot with the instrument scientists and learn a lot. So there's an strong educational component that I'm very grateful for in that respect, in these collaborations. And of course, acknowledge my students, particularly these students highlighted that helped make the compounds shown. And this is just pictures, cool pictures in the new chemistry building we moved into several months ago. And I'm happy to take any questions.
We've got robots to make materials.
We're not quite at robots.
Not according to the robot.
Thank you for the nice talk. I think the compound was iron selenide. It's twisting, right? When you synthesize. Do you also see Moiré patterns because of the twisting?
No, the reason we don't see really that is the angle is I think the angle is too big. So what we see instead, are these nice like superlattice reflections and so forth, but we don't really see Moiré patterns. That's a very interesting thought because of course bilayer twisted graphene is superconducting. And it's something that I think should be followed up on with iron selenide, either, by physically doing it. Chemically, I don't think we could make something with the small angle like that, where the smallest we can get to is like 26 degrees. Yeah, twist. So, yeah.
Yeah, thanks for interesting talks. I have the simple two question. Is the iron sulfide and selenide air sensitive, like black phosphorus or indium selenide?
No, it's not. Iron sulfide is a little bit more because it's in a metastable form of iron sulfide in this layered form. If you go above 200 degrees Celsius, it'll decompose into a variety of iron sulfides. Iron selenide is a bit, in that layered form, is a little bit more thermodynamically stable. You actually have a window in the phase diagram where it exists. But I would say, don't leave it out for a whole year. But, for a couple of days or weeks, it's fine just being out. And we try to keep everything in the glove box and in any case for precaution, but it's not particularly air sensitive, no. Yeah.
The other question is there any possible way to get a thin layer and monolayer and bilayer generally using the Scott-Say method?
I think for iron selenide and sulfide, without intercalated species, probably yes. As soon as you start intercalating things, all the molecules and layers that we intercalate are charged. So there's Coulombic, attraction between the two, and I think those would be very difficult to exfoliate. But I believe people have done it for iron selenide. I don't know about iron sulfide. Yeah.
If I could ask you a quick question.
Oh, yeah.
How do you have those harsh conditions, high pressure, and get that freeze in and out? I thought you'd have to have a containment system that would be...
Yeah. When we first started doing this, I had read the literature and people had designed a setup with sapphire windows and everything. And I thought, why don't we just, I worked with Wen Cheng and others here, right? And we were like, okay, why can't we just do a simple tube? And there were others, I think like Kirill Kovner, who had done it as well. And it turns out that the tube doesn't rupture. And we were able to do the solvothermal hydrothermal just fine. They're not too high in pressure though, right? We're not going super high in pressure. So I think that's why.
If there's no more questions, let's thank our speaker. Next, Suyin Quick, places are right. And come all the way from Singapore. All the way from Singapore, National University of Singapore. Give us a talk. You have 10 extra minutes, so just don't break down.
Okay, thank you. I may. Thank you. I need a clicker. Yes. Thank you. Right. Good morning, everyone. It's a pleasure to be here. And first, I'd like to thank the organizers for inviting me, and especially to Pierre, whom I've known for, I think, more than 10 years now. Yeah, and if Maria is here, I also know her for quite a while. Thank you also to Connie and Kate and Kim for helping me. So I'm very delighted to be here at Argonne at the APS. It's also a place that my husband frequents, and he really enjoys his time here. And he's with the kids today, yeah. Okay, so today I'll be speaking about light-matter interaction in nanoscale materials, and I'm a theorist, a computational person, so it's a slightly different flavor from the previous talks. And this is something that all of you know, but it's just to set the stage, because I'm going to start off with going through a little bit about the basics of the methods that I use, and then after that it will be all about the results. So when light interacts with matter, all sorts of things can happen, and we have heard some of this in previous talks. What I'll be focusing on is the charge-neutral excitations, where an exciton forms, like so, with the electron and hole forming a bound state. And in nanoscale materials, because of reduced Coulombic screening, these electron and hole interactions, the Coulombic interactions, are significantly larger. And excitonic effects are very interesting in nanoscale materials, and I'm just going to point out three broad areas of applications. The first is quantum technologies, where you have light being used as a tool to control the quantum states of defects in materials, and we can also use materials to generate single photons or entangled photons. And then, of course, we have energy and sustainability. I will be talking about bulk photovoltaics later on, based on nonlinear optics. And finally, in the last part, I will not have time to touch on this, and you've heard some of this yesterday. Excitons are also useful for the next generation of devices. So when I say we use first principles approaches basically try to solve the many-body Schrodinger equation without any empirical parameters, but with some well-defined approximations. And if we look back in time, the first quantitative calculations for electronic states was actually done before the invention of the computer. Took 10 data points over 10 afternoons by Wigner and Seitz, right? And then fast forward to 2010, one of my colleagues was able to run the calculation on a smartphone, getting the electronic structure of silicon. And then in 2020, we can even get excited states of huge systems running on 10 minutes, right, on a supercomputer. And this is where my relationship with CNM comes in. So I am using the computers here for some of this work. And in terms of the breadth of first principles approaches, there are quite a few. The workhorse of first principles calculations is what you have heard several times in the workshop. So DFT, which stands for density functional theory. And this is where we try to simplify the problem of interacting electrons by considering the charge density. And there are theorems on which this is based. Now, DFT reliably predicts total energies. So you can get thermodynamics, kinetics, phonons, okay, but it is really not meant for excited states for quasi-particles. Constrained DFT, where we actually constrain the occupations of states, can give some reasonable estimates for the zero phonon line emissions. We'll have some of that later. And there is also a very broadly used approximation called single particle approximation. And in DFT, this comes about in what we call the Kohn-Sham formalism. And the particles are really fictitious particles. And with that, we can get qualitatively accurate band structures, but not quantitative predictions of these band structures. Right, and we can go beyond that to many-body perturbation theory with what we call the GW approximation, where we really look at the physics of quasi-particles, real physical quasi-particles that are, in this cartoon from the textbook, we have for example, the electron that is screened by a constantly changing cloud of electrons and holes. And because of this cloud around the electron, the interactions between these particles are a lot weaker than in the original many-body problem. And this is because we have the screen Coulomb interaction, which usually is approximated by W. And then when we talk about light-matter interaction, you saw just now in the cartoon, we have the electron and the hole, so it's actually a two-body problem. And this is typically solved using the Bethe-Salpeter equation, where we have the electron-hole kernel that takes into account the interactions between the electron and hole. And the exciton state is a coherent superposition of these individual electron-hole states. And this exciton envelope function that I label here as A will become important in the last part of my talk. So the GW and Bethe-Salpeter approach can quantitatively predict the exciton energies and states in materials. So this is going to be my outline. I will broadly talk about quantum defects in 2D materials, and then also the nonlinear optical response in the excitonic regime. And for quantum defects, there are interests in quantum defects for single photon emission, as well as spin qubits. So these are the more common applications that we have. So although defects are sometimes problematic, they can also be useful. Now, why quantum defects in 2D materials? Well, they are easier to access and they allow for better integration with photonic chips. And we really don't want defects to be appearing randomly, and we don't want to have to guess what we are looking at. So the holy grail, if we are trying to make use of defects for applications, is actually to know exactly what kind of defect we are looking at. Of course, this is where all the imaging, experimentally, spectroscopy becomes important. And we want to be able to synthesize the required defects and eliminate unintended defects, and also control the quantum state. So there has been a lot of progress. So the ones that you see here are advancements in methods that are used to identify the defect, both experimentally and theoretically. And then also for synthesis, nowadays we are able to controllably incorporate desired defects and also passivate unintended defects. Now, hexagonal boron nitride is a system where single photon emission has been studied widely. It's been observed by many groups. Okay, but the problem with this system is that the nature of these emitters is quite unclear. And this is just to give an example. So we have emission at 2 eV from different groups, and probably they are not all the same defect. So we want to move towards, like I mentioned, control creation of single photon emitters in HBN. And one of the ways that is popular in the literature is to use ion beam or electron beam manipulation to actually create defects. And it has been shown that usually it is the boron that gets knocked out of the lattice. Now, when the boron gets knocked out, of course, you form a vacancy and you have the boron interstitial that's going to migrate. So the boron vacancy, it tends to be negatively charged, is actually a widely studied defect in HBN, characterized experimentally and also theoretically. Okay, and we have also done some work on this. But although that has been the case, what has actually been frequently assumed in the literature is that the boron interstitials are not interesting. Well, not interesting because boron interstitials, especially the neutral ones, they diffuse quickly. At room temperature, they would diffuse quickly, and it is likely that they would actually combine with a boron vacancy and be done with that. But my experimental colleagues actually observed boron interstitials after ion bombardment, and you can see that in red over there. Yeah, and I think importantly, they were also able to observe blue emission in areas that were microns away from the regions that they irradiated. So that tells us that whatever area they were irradiating, something happens elsewhere. And it is very likely that this is due to the boron interstitials diffusing out. And so here are some PL spectra that you see there. And there's a 2.8 and 2.7 EV deduced to be the zero phonon lines. Right, and the emission from VB minus, which is, I mentioned, a commonly studied defect, is observed, but only at the irradiated points. Okay, so we were very interested in this to look at the role of boron interstitials in single photon emission, what kind of excitons you can have, and importantly, it looks like this is something that we can create intentionally. So what are some possible defects? Well, the neutral interstitials are mobile at room temperature. The charged ones, they do have a diffusion barrier, but high energy, they do have high energy from the bombardment, so they could diffuse. And we know they're not going to be stable for a long time at room temperature, but they can combine with existing defects, right, to form defect complexes. So we studied some of this. Carbon is a very common unintended defect in HBN. So we took a look at boron interstitials combining with carbon. We found that they are kinetically and thermodynamically stable. And we also predict that they are bright emitters. And we thought that it seemed that boron with carbon at the substitution nitrogen site could be a possible emission for what was explanation for what was observed in experiment. Of course, there's a lot more to be done to really make that statement, and I would really frame it more as a prediction that we can create these complexes and they are bright emitters, which can be potentially useful for single photon emission and other applications. So we talked about HBN. Again, HBN is a wide bandgap system, so very popular for room temperature applications. We heard a little bit about the TMDs, transition metal dichalcogenides, and these have smaller band gaps. But they are also useful because with a smaller band gap, you can gate the system more easily and control the system. But yeah, of course, lower temperatures are involved. So single photon emission has also been observed from TMDs by several groups. So what kind of defects do we have in this TMD? So theoretically, it's found, and also experimentally, that usually it's the chalcogen vacancies that are the most common defects in most of the synthesized TMD materials. And these are some SCM images, right, of them. Quite some time ago, we worked with my colleague Andrew Wee and Stephen Panicook at NUS, and we found that actually, although vacancies are predicted to be the most common defects, we couldn't see the vacancies in our STM images in tungsten diselenide. So this was done by a student of mine who was also doing experiments with Andrew Wee at that time. So there were no gap states at all, and the vacancies should have gap states. So after a while, and we will see the STM images later, but what we found is that O2 can dissociate at the vacancies very easily, and at room temperature, it should dissociate. And even if you do have synthesis with oxides, we do expect also oxygen to be substituting the selenium vacancy. So what we have found is that oxygen tends to bind to the selenium vacancy and passivate the gap states. And then you have the interstitials and atoms forming, and none of these have gap states. And the STM images do match well with experiment at multiple bias voltages. So you can see them here. We have the three most common defects observed in STM, and we were able to reproduce these using the oxygen-related defects. So we are quite confident, and other groups have also found that oxygen is present and substitutes the selenium vacancies. Now, you saw just now the sulfur vacancies in MOS2, so why is it different? Well, it's slightly different because WSE2 actually has a lower work function than the MOS2, and that actually facilitates charge transfer to the O2 anti-bonding orbital and facilitates dissociation. Okay, so this also has implications for Schottky barriers and so on. So it's nice that actually we know that there will be no gap states coming from these unintended vacancies in these systems. But these are also materials, actually for, in particular, WSE2, where the single photon emitters were observed. There were 4 papers in 2015 on this. So it could be that it might be coming from the oxygen interstitial, where we do actually predict a localized exciton at around the same energy at what was observed in experiment. So now that we are quite pleased that we don't have gap states from the selenium vacancies, how then can we introduce the effects that we desire in the TMD? So there has been a lot of progress in scalable synthesis where transition metal impurities are substitutionally doped into TMDs at the TM sites. All right, so these are various experimental evidences that you can find done by my colleague Goki at NUS. And we have also observed emission from these defects. So what I'm going to focus on when talking about the transition metal substitutional defects is not single photon emission anymore, but we will be switching gears to talk about spin qubits. Spin qubits, of course, is something that Julia Gali here in Chicago does a lot of, and I've just actually gotten into the field. But there are 2 ways that spin qubits are controlled optically in the literature. So one is what we are familiar with that you see on Wikipedia for the NV center in diamond. And this is through inter-system crossing, where you have a crossing between the triplet state and the singlet state, and it is spin selective. Okay, and so with repeated pumping, you are going to be able to achieve a state with a single spin sublevel. And so this allows you to operate the qubit at room temperature, but actually with lower fidelity. And with the same NV center in diamond going to low temperatures at 8.6 Kelvin here, experimentalists have also been able to report much higher fidelity by using the resonant optical excitation method common in atomic physics. Right? So here you have spin conserving transitions, and you just use resonant optical excitation to control it. Okay. So can we have higher fidelity and higher temperature? One possibility is to use the resonant optical excitation method, but to actually try to increase what we call the zero field splitting between the MS sublevels in the triplet state. And this firstly will increase the difference in the resonant frequencies, so allowing for better resolution. It also reduces the phonon-mediated transitions, which would have an impact on your spin relaxation times, and even also the spin coherence times if you're able to control other types of defacing. And it can be done here with dynamical decoupling techniques. So what we found actually is that And the reason all this came about was that when we were looking at these substitutional defects in TMDs, we found that the zero field splitting was actually quite large. This was in the terahertz range. And the question is, can we then move into the realm of quantum terahertz technology? So terahertz technologies have been the focus of quite a lot of funding these days, but mainly in the classical regime. And the question is, can we actually have optical control of spin defects that have a zero field splitting in the terahertz range? Because that's not obvious. And this might potentially lead to more robust spin qubits operating at higher temperatures with higher fidelities. Okay, the other question that we had was that when you have the defects, the quantum defect, you could also think about single photon terahertz emitters. So there have been emissions, microwave emitters reported using the ZFS before in silicon carbide. So these are two areas that we were interested in, and we like I said, we found large zero field splittings, mainly coming from the spin orbit coupling effects. Okay. Before I go to the next slide, I just want to say that this was done using sort of like a high throughput approach, looking at 50 different systems, each with different charge states. So with that, we identified these systems as spin triplet systems that can be achieved. And part of this work was done at the carbon cluster in CNM. So I'm going to focus on two of these that can be controlled optically. And the first is a system which is a triplet state, and the singlet state is actually much higher in energy, so it doesn't have inter-system crossing. And the advantage of such a system is that it allows for better resonant optical excitation control because there is no sort of leakage, if you will, to the singlet states. And that is good for the spin qubit fidelity. Right. And then the other system that we did find was one that had shelving singlet states. And in this case, we still can have the spin qubit, but at the same time, we can think about a possible single photon terahertz emitter that comes because of preferential coupling to the lower sublevel of the excited state. Right, so we can do all these kinds of different exciting things, but it requires the fields of the quantum defect community and terahertz community to come together because most of the experiments are set up for gigahertz ZFS, all right? But there's plenty of room for progress. Okay, so that's my story for defects here in the 2D materials. And next, I'm going to talk about nonlinear optics in the excitonic regime. And this is where we have generation of entangled photons using spontaneous parametric down conversion. And I'll talk a little bit about shift currents as well. So nonlinear optical properties basically is, for example, like I showed here, the polarization depends nonlinearly on the electric field. Okay, and you can get all sorts of different effects. So there has been significant interest in nonlinear optics in 2D materials specifically because it has been found that the nonlinear optical response is larger in 2D materials than what you imagine. And secondly, nonlinear optics has recently become very interesting from a theoretical standpoint as a probe for quantum geometry. And so experimentalists also try to use nonlinear optics to probe quantum geometric properties related to the band topology. Now, why am I interested though in nonlinear optics in 2D materials? Well, it actually is technologically interesting because in bulk materials, you have what we call the phase matching problem that reduces your signal and you need delta KL to be very small. If L is 0, then of course you do not need delta K to be small. And potentially 2D materials can be interesting for nonlinear optics. But there was the question as well because of the volume shrinking, right? So what we want to say here is that when the thickness shrinks, it is not that the chi, the susceptibility remains the same, but it actually changes significantly because of enhanced excitonic interactions. So this is an example of strong excitonic effects in 2D materials that you see here in MOS2. And nonlinear optics has been traditionally described within what we call the independent particle approximation, and a lot of good work has been done in this area. Textbooks have been written, but it does not take into account the interaction between the electron and the hole. So the question then is, if we take into account the excitonic interactions, do you get qualitatively different results? And how do we understand the fundamental origins then of nonlinear optics in the excitonic regime? And can we accurately predict the response? So we developed an approach to quite efficiently compute the second order nonlinear optical susceptibility. And this is quite a bit of a messy slide, but you can see that the important quantity here is actually the matrix element between S and S prime, two exciton states, which is absent in the linear regime. Okay, the first part that I'm going to touch on is sum frequency and difference frequency generation, or in particular what we call the second harmonic generation and spontaneous parametric down conversion. And the material that we looked at, just a shout out here, was actually NBOX2, which we got interested in because of one of my students who was interested in high throughput projects. It's really not something that I do a lot in my lab, but yeah, working with the student, we actually discovered something fun. And this is actually how my interest in nonlinear optics got started. So we found that NBOX2 was identified as the ideal 2D piezoelectric and was synthesized experimentally as well and measured. So this is the atomic structure of NBOX2. The nice thing about it is that the polarization direction is the same for every layer, and so it just stacks up. And because it lacks inversion symmetry, and that's an important part of seeing the nonlinear optical response, we studied this for nonlinear optics. And if you calculate the susceptibility here, we can see that comparing the excitonic case in black, right, with the case without excitonic interactions in blue, there is a huge difference. There is an enhancement coming from the excitonic interactions. And the excitonic resonances themselves would enhance your signal, of course, and you can see that here. We also demonstrated that, you can have resonances both with the omega and the 2 omega part, and you can also have a double excitonic resonance if you'd like. And so this is where I think the theory comes in to help to guide experimentalists on how best to optimize their signal and get a stronger signal. So with a double excitonic resonance, you actually can get an even larger order of magnitude enhancement of your signal. Now, comparing with experiment, I think was actually very interested to see that there is a qualitative difference in the SHG signal with and without the excitonic interactions. And of course, when you have the excitonic interactions, the comparison with experiment actually becomes a lot better. So these are polar plots taken at different energies for the SHG signal, and the black is the case with excitonic interactions, the blue without, and the red dots are the experiment. So in these polar plots, not just the intensity, but also the phase, the relative phase of your susceptibility becomes important. And that really determines your shape. So you can see that excitonic interactions do result in a qualitative change that is required for better comparison with experiment. And just to add that we actually are able to reproduce these when we shift the energies a little considering that there may be a little bit of error in our energies. So I think that was very interesting for us, and to actually compare the experiment. Now next I'm going to talk about something different, which is a shift current, and that is, instead of a sum frequency or a difference frequency, we are actually looking at the limit of a difference frequency where the final frequency is 0. We call it a static response. And in fact, it's a DC current. So shift currents are interesting as a next generation solar cell going beyond the Shockley-Queisser limit. And from a theoretical standpoint, and even for some experimentalists, it is very interesting that we are actually able to see some quantum geometry arising in the physics of shift currents in the independent particle picture. So here you can see that there is a shift vector associated with the shift current. That over there, the big R, and it is related to the change in Barry connection of your single particle bands. Now, we were very interested to see what will happen when we bring the formalism to the many-body regime. And our many-body shift current conductivity was calculated in 2 gauges. Okay, they are actually equivalent, but the different gauges allow us to actually distill different physics from it. So the first one on the top there, from the velocity gauge, you can see that your sigma becomes large, right? When you have a large term 2, especially when omega s and omega s prime are close in energy, what we call nearly degenerate excitons. So when we have regions of nearly degenerate excitons that are actually coupling through the matrix elements, we do expect a large shift current conductivity. And this can be manifested later in the results when you see that when you reach the case of resonant excitations, your shift current conductivity goes up. Now, the second one, which is the length gauge, is where we actually see something like a shift vector coming up as well, and I call this a many-body shift vector, where you actually look at the difference in the R, the position of from the ground state, stator determinant, to the excited state. So some first principles calculations to compare with experiment. Again, this is bulk cadmium sulfide. And the reason I chose this particular experimental data is that it was performed at 2 Kelvin. And this is therefore where the shift current will dominate, because there is also discussion in the literature about ballistic currents, right? So here the ballistic current should be small, and you can see that the shift current conductivity is observed below the band gap, below the quasi-particle band gap. And comparing experiment with theory, I think the agreement is not too bad. And we also were able to analyze the shift vector, and that helps to tell us the origin of what we are seeing. So you can see here that the what's happening below the gap coming from Y1 and Y2, shift vectors are shown, and that comes from the excitations close to the gamma point, and actually these are nearly degenerate excitons. Okay, so this is really a zoom in, and in order to actually get this plot, we had to really sample the Brillouin zone very finely near the gamma point. Right. Yeah, so nearly degenerate excitons were important for this below band gap shift current conductivity. And then we also computed the shift current conductivity in monolayer MOS2. I don't have the experimental plot here, but I do have a colleague who studied this, and the agreement is actually not too bad as well. There is, therefore, you can see a large enhancement coming from the excitonic interactions. So where does the enhancement come from? Well, it can come from multiple origins, but I want to analyze it within the concept of the many-body shift vector. So if we write out the many-body shift vector, we can actually have see it like this. So the first line there has what we call the IPA shift vector that people have studied for years. There in blue, the R. Now the first two terms, let's say they're not so important if we are considering just a single V to single C transition. So the IPA shift vector there is then what we call renormalized by the envelope function. Okay, so recall that the exciton can be written as a coherent superposition of interparticle excitations. So, and A will be your coefficient. So A there, is normalized, right? So the summation of magnitude of AS squared is 1. So therefore, you can see that the renormalized IPA shift vector cannot be that much larger than your original IPA shift vector in the independent particle approximation, right? Then you have a second part which looks very geometric, right? But it's a weird kind of geometric property because normally when we talk about band topology, we are looking at the geometries of the faces of single particle states. And even for excitons, when we're talking about quantum geometry of excitons, we are usually talking about delta A, delta Q, where Q is the momentum of an indirect exciton. But here we're looking at a new kind of geometry, which is the geometry related to the envelope function and how that envelope function is changing with K. And this even looks a bit like the Berry connection in some sense. So I'm just going to move to the next slide. Some results here. In dash blue, we are plotting the first part, the renormalized shift vector from the independent particle approximation. And then you can see that it's actually the geometric term that leads to the order of magnitude change or enhancement in your many-body shift vector. Okay, and like I said just now, the geometric term can be described really as an integral over the Brillouin zone of a kind of connection of the exciton envelope function. And the integral is actually taken in the direction alpha of your shift vector. A shift vector has a direction. And so this is actually a very new physical phenomenon that we are quite excited about. And it takes quantum geometry to a new regime. And it's also responsible for enhancement of the shift current. So with that, I just want to summarize and actually also look ahead. So I've talked about quantum defects and the nonlinear optical response. I've chosen these because they are relevant to my work here as a user in CNM. For the quantum defects, we talked about structure property relations and predictions for quantum terahertz technologies. Part of this work was done by my student using the CNM facilities. As for the nonlinear optical response, we are working toward looking at shift currents of orbital magnetic and spin magnetic moments, and this is ongoing work in the CNM as well. So thank you very much. And I want to acknowledge my group members who have done the work, my senior collaborators, funding, as well as the computational facilities here in CNM, as well as back in Singapore. Thank you for your attention.
Thank you so much for the talk. So I have a question about the excitonic enhancement of the nonlinear response in polar mediums like you showed. Is there a fundamental trade-off because of the polar material has a high dielectric function?
Sorry?
And because of that, can you hear me well?
Fundamental trade-off because of?
Because of the dielectric function of a polar medium versus the exciton binding energy. In a polar medium, excitons will be screened more so that the effects you show might be more or less pronounced because the exciton is a much weaker bonded. Like, is there a fundamental trade-off to study this in a polar medium versus non-polar medium?
Yes, so definitely the environment matters, and all my calculations are done sort of in vacuum. And yes, if there is additional screening, then I think the excitonic effects will become weaker. So, but just now you saw in bulk cadmium sulfide where you can see a visible effect due to excitons even in the bulk. But if you're talking about enhancements, then you do have to go to nanoscale materials. I would say a trade-off might be also that it is still true that when your material becomes thinner, you have less signal. So that is a trade-off, but then it is a linear versus order of magnitude enhancement. Yeah. Thanks.
Thank you for the great talk. I had another question about the nonlinear enhancement. Are all excitonic states associated with, a larger nonlinear response, or is that just some specific excitant with some, particular envelope function or some particular underlying state where you see the enhancement?
Yeah. I don't think that it is true for all excitonic states because there's also the matrix elements that we have to take care of. So first of all, it has to be bright. So there's a matrix element P between 0 and S, and then there's also PS to S prime. So the matrix elements are important too. But interestingly, that's a good question because if we talk about the linear response, there is a sum rule that governs the oscillator strengths, right? And so, you can't really get enhancement everywhere. There'll be enhancement at some energies and not in the others. But for the nonlinear optical response, we were not able to find such a sum rule. So it looks like for nonlinear optics that there is a chance that you get larger enhancement overall, but I wouldn't say that it's for every energy. Yeah. Thanks.
Thank you.
All right, this one is a naive question. So what is the difference between a shift current versus optical rectification?
Oh, great question. So the shift current and optical rectification, they are both part of your static nonlinear response. But the shift current is the current, whereas the optical rectification is the voltage. And you should be able to see both. Yeah. Thanks.
Okay, I guess if that's all the questions we have, I think everyone's ready to bolt for lunch, right? So let's take a break, and then we have our respective user sessions at 1 o'clock. Is that right? 1:30. All right. Let's thank the speakers, all the speakers. One last time.